Okay, so what we saw just a few minutes ago was that we reduced the question of understanding when is it that the semi-network programming achieves exact recovery to the question of whether the deviations from its expectation of this random matrix are controlled by a certain term, alpha minus beta over 2 log n. And so we developed a few weeks ago a method, or we studied the matrix concentration inequalities, which are ways to controlling exactly this. Right? They control exactly the deviations of a random matrix from its expectation, but only for matrices that are written as sums of independent random matrices. Right? And this a priori does not look like a sum of independent random matrices, but this is a great illustrative example of how many matrices actually, random matrices, even though they might not look like a sum of independent matrices, we can often write them as a sum of independent matrices. Right? So before I go into the stochastic block model Laplacian, let me just do it with the normal Laplacian. Let's say we have a random graph, which edge shows up with some probability, or each edge has some weight that is random. Right? Then remember the Laplacian was given by some, maybe y smaller than j, of wij, ei minus ej, ei minus ej transpose. Right? So now if all the edges showing up while their weight is independent, we effectively have written the Laplacian as a sum of independent random matrices, right? Because this is now a random matrix because the weight is random, meaning it's 1 if an edge shows up, 0 otherwise. And right, this is just a matrix, so this makes this a random matrix, even a sort of a random matrix series, but okay, we don't even need to get it there. This becomes a sum of independent random matrices. So even though the Laplacian doesn't even have independent entries, right? The diagonal for sure is dependent on what happens of diagonals. Still, we can write it very naturally as a sum of independent matrices. And so we're going to do exactly the same for the stochastic block model, right? We're going to just have to adapt this a little bit. But essentially, for the stochastic block model Laplacian, a very, very similar thing is happening, right? What is this matrix? This matrix has 1, minus 1, minus 1, 1 in the entries ij. Right? Well, we have to do this for the entries ij when they're in the same community, and they're in a different community. We just have to put minus 1s everywhere, right? Because we still get a minus 1 in the Laplacian, but we get a contribution of minus 1 to the diagonal. So all we have to do is to come up with the decomposition that uses these matrices rather than these ones, right? But it's actually quite easy, right? So we define for I and j in the same community, right? So we can write this as gi equals to gj. We define gamma ij. This is going to be a random variable that's going to say if there's a node there or not, right? Plus, okay? And so this will be 1 if I and j is an edge, right? If I is connected to j, 0 otherwise. Okay, but only for those that are the same, right? And what's the corresponding matrix? The corresponding matrix is exactly this one. Right, so let me write that. Right, so the corresponding matrix will be a delta ij plus, to be just equal to ei minus ej, ei minus ej transpose. And for ij not in the same community, we define the same things. Gamma minus ij as being 1 if I is connected to j, right, if they're an edge, 0 otherwise. And the matrix now is the matrix where it gets 1s in the diagonal, minus 1s in the diagonal, minus 1s in the left diagonal, so this is just equal to minus ei plus ej times ei plus ej transpose. Right, and now it's easy to write. The stochastic block model Laplacian is just given by LSBM, right? It's just equal to what? It's just equal to the sum for all, say, I smaller than j, such that gi is equal to gj, right? Of lambda ij plus delta ij plus, right? Plus the same thing for the off diagonals. Right, so lambda ij And here we can include the loop. I mean, it doesn't really make any difference. Minus, right? Because in the loop, when I is equal to j, this is just 0, right? So it won't make any difference, but it makes some of our calculations a little easier. So it doesn't matter if we allow the loop or not. Okay, so now this is a sum of independent random matrices, right? Because these random variables are independent, right? They're jointly independent because each edge shows up with a certain probability, but it's fully dependent. Most of the G is fixed. And these are just some deterministic matrices. So now this is a sum. This is a sum of independent random matrices. Right, so now this is a sum of independent matrices, random matrices, so we can use matrix Bernstein. Right, we can use matrix Bernstein that we saw a few weeks ago. Right, matrix Bernstein inequality. Right, so for matrix Bernstein inequality, let's write it here. Okay, so the inequality says for xk and family, okay, this n is not going to be, let me use big N. Xk, k from 1 to big N, a family of independent d by d symmetric random matrices. Right? Then they need to be centered. Right? Which these ones are, but we're going to take away its expectation, so it's okay. They need that the maximum eigenvalue of all of them is smaller or equal than R for almost surely. And we define sigma squared as this variance parameter, right? Which was the expected, I mean, it's easier to write this way, sum the expected value of xk squared. Right? And then the inequality said the following, that for all t bigger than 0, we get that the probability, right, of lambda max of the sum of the xk's being bigger than t was bounded by, or bigger or equal than t, was bounded by, there was this dimensional factor d, and then there was an exponential of, at least if I get exactly all these terms right, minus t squared over sigma squared, maybe with the 2 sigma squared plus 2/3, 2 sigma squared plus 2/3 RT. Okay, and now, we're going to control, of course, our matrix doesn't have mean 0, but once we remove its expectation, it will have mean 0, right? So that's okay. So we're going to take this minus its expectation, so basically we're going to write this gamma is minus its expectation, so that's fine. Now we actually want to control the spectral norm, so not just the deviation of the leading eigenvalue, but also of the smallest one. Right, but that's okay. We can just use the inequality on minus xk, for example, right? So as long as R is a control not only on the maximum eigenvalue, but on also the negative one, so we're going to instead control the spectral norm of sk, then we can just use the inequality on both sides, right? This will be this, and then use the union bound, and we'll just get an extra factor of 2 here. Right, so if R controls actually the spectral norm of xk, and we put a 2 here, we're allowed to control the spectral norm of this. Okay, so that's going to be the strategy. We're going to try to understand these matrices, right? So let's go and do this. Okay. Let me erase this part. Okay, if needed, we'll go see what these variables are again. Doesn't really matter. Okay, and let's write L minus LSBM minus expected value of LSBM. So LSBM minus its expected value is equal to, again, sum, I smaller than j, or smaller or equal, doesn't matter, gi equals to gj. We do lambda I j plus minus its mean, right? But what's its mean is the probability that we see an edge. Right? So it's n, the probability that there is an edge. So it's alpha log n over n, right? Alpha log n over n times the corresponding matrix plus sum over I smaller than j, right? And here we can consider this gi equals to different than gj of same thing, right? I minus is now beta n and now delta g. All right, so now we can use matrix Bernstein. We just have to understand what R is, right, and sigma squared. Right, but we have to understand to use now matrix Bernstein. Clearly they are being zero, they're independent, and so on. We have to understand what is R and what is sigma squared. Right, so for sure, these random variables take values, right? These random variables only take values between -1 and 1. Right? So, right, for sure, they only take values between -1 and 1. Same thing for this. Right? They're like either 1 minus this little bit or minus this little bit. And now, so the spectral norm of each one of these matrices is always small or equal than the spectral norm of one of these one of these big delta matrices. But what is the spectral norm of, say, delta plus ij? Right? It's just the spectral norm of, ei minus ej transpose. Right? But this is just the L2 norm squared of ei minus ej, which is square root 2 squared, right? So this is just 2. Right? We have this vector is on root 2, so there's another root 2 coming from here, you get 2. And the same thing happens for, this is the exact same thing happens for the spectral norm of lambda minus. Right? For the lambda minus, you get a plus here and a minus there, but it doesn't change anything on the norm. Okay? So what this means is we can take R to be equals to 2. Okay, so we're making progress. So R is now taken to be 2. Now what we have to compute is sigma squared. Right, so let's try to compute sigma squared. Okay, so sigma squared, let me erase all of this. Because once we compute sigma squared, we can plug in this inequality. Right, so I'll try to compute sigma squared without using this, without erasing this, using this part of the board. Okay, so what we have to do is to write, now it will be the spectral norm of the sum of the squares in expected value of these matrices. Right, but the expected value of the square of this is just the variance of this variable. So what we can write sum for I, say smaller than j, again, smaller or smaller or equal is all the same. The gi, maybe I'll try to, we might need the space here. So gi equal to j of variance of sigma ij plus times this matrix squared plus the sum of I smaller than j, gi different than gj, variance of this times this matrix squared. Okay, so this is what we need to control. All right? Now, of course, the variance of all these terms is the same, so we can move the term of the variance to outside of the sum, right? Because it's the same for all I and j, as long as it's, as long as I and j are either in the same community or different community. So really what we have to understand is we have to understand these quantities, right? We have to understand the sum for delta I, okay, let me try to do it here. We have to understand the sum for delta ij plus, for I, gi, right, for I, say smaller than j, such that gi or smaller or equal, again, is the same, gj squared. We have to understand this matrix, and the same thing for minus, right? Because once these terms come out, we have to understand the sum, right? I mean, this is just basically calculus, right? A little annoying, but it's just a calculation. Now, let's think about what this matrix is, right? This matrix is EI minus EJ times EI minus EJ. When we square that, we simply get twice that, right? When we square this, we get this times this. There's an inner product here that gives a 2. So we just get we just get 2 times what we did. So it's just twice the same sum of lambda ij plus. Right? But now what is lambda ij plus? Lambda ij plus is a sum that for every pairs of nodes in the same community puts a 1 in the diagonal element and a minus 1 in the edge. But if we do that everywhere, and if we assume, that we have, say, G being plus here and G being minus here, right? So we're taking, without loss of generality, just to see what the picture looks like, we are making the first half of them be one community, the second half be another, and so on. If we do that, what we get there is we basically get minus 1s everywhere, right? Except for the 2. The 2 will go like this 2 times. Minus 1s everywhere, except in the diagonal we get a contribution of 1 from every little thing, right? So we get like n over 2 minus 1 in all the diagonal elements and 0 here, right? So what is this? This is just equal to 2 times, right? N over 2 identities, right? Minus the matrix that has 1s in these diagonal 0, 0s, 1s, right? So this matrix, we know what it is, right? This matrix is just half of 1, 1 transpose plus GG transpose, right? This we've seen a few times, right? So this means that I can write that as 2 times, right? I can write this, and again, expand this out and check. You should check for yourself. I get, this is twice this quantity, so it's twice, n over 2 identities, so it's just n identities, right? Minus this matrix, half of this matrix, but twice that. So minus 1, 1 transpose plus GG transpose. Okay, so now what about this one, right? This one we get E, right? So what is this matrix? This is minus EI plus EJ times EI plus EJ transpose. So it's a matrix with minus 1 in the diagonals and minus 1 in the off diagonals. If we take the square of that, the 1 goes away, right? And we get 2, and then the matrix says just 1s in the right sum, and then basically the minus lambda ij, right? Because before it was all minus 1s, when we square is all 1s. So really what this matrix looks like is we're going to have exactly the same behavior here, right? So we get an n over 2 in the diagonal, which is a contribution from every pair I and j in different communities. For every node I, there is n over 2 j's in a different community, and then we'll get 1s everywhere and 0s here, right? That's what this matrix looks like. Right, and so what is this? This is still n over 2 identities, but now it's plus the matrix at 0 here and 1 there. Right, but the matrix at 0 here and 1 there, what is it? It's simply 1, 1 transpose minus GG transpose, right? And since we're taking twice of that, right, because we have the matrix minus 1, minus 1, minus 1, minus 1, when we square it, it gives 2, 2, 2, 2. Then the matrix we get is, okay, so let me erase everything, is n identities plus this minus that. Okay, this is the kind of thing that you should look in the notes or just check it yourself. But it's n identities plus 1, 1 transpose minus GG transpose. Okay. Okay, so now we have these matrices. Now we're ready to compute what that quantity is. Right, because what is this quantity? This sigma star is, the variance of this times this sum, which we know what it is, plus the variance of this times this sum. Right, so actually let's just, erase this and, use these things to just write what this is, right? So this is sigma square is now equal to, okay, so we get the variance of this term, times this matrix, right? Plus the variance of that term And I mean, for any ij, the variance is the same times this matrix. Okay, so we're almost there, right? I was trying not to erase the inequality, but okay, so we're almost there. So let's see. So r equals 2, right? The board isn't so big. So let me keep r equals 2 here. Okay, now, all these matrices are positive semi-definite, right? They're sums of squares. Each term is positive semi-definite. So we can bound this, we can replace the variance by something a little bigger, right? That will only make this quantity bigger because there's no cancellations, right? All these matrices are positive semi-definite. You can see this by the fact that we took squares of symmetric matrices. Also, you can see by the fact that here we're having eigenvalue n, we're summing another eigenvalue n, subtracting an eigenvalue n somewhere else. So this for sure is a positive semi-definite matrix, and here as well. Right, but they're sums of squares of symmetric matrices, so they have to be positive semi-definite. And it's not hard to see, right, the variance of, say, a gamma plus, right? This is a Bernoulli that has probability alpha log n over n of being 1, and the rest of being 0. So the variance is alpha log n over n minus the square of that, right? So in particular, it's smaller or equal than alpha log n over n. Now, we're losing this square of that quantity, but if you think about it, that quantity is like alpha log n over n squared is something like 1 over n squared, so it's way, way smaller. So it's not so bad to just replace this by, alpha log n over n. The loss we're making is much lower order, right? It's in the order of n squared, right? The variance of minus, right? Same thing for minus is beta log n over n. Okay, so what this means is that sigma squared is smaller or equal than the spectral norm of, okay, now let's try and collect terms. Let's try to do this properly. So we can replace this by alpha log n over n and this by beta log n over n. So let's see how many identities we have, right? How many, okay, let's see how many identities we have. Let's do it like this. How many identities do we have? We have alpha log n over n times n, right? So this is alpha log n, right? Times n over n plus beta log n over n times n, so plus beta log n. Okay, so now what about say 1 transpose, right? So we get okay, so for 1 transpose, what do we have? We have minus, right? And now we get alpha log n over n, right? But here is a plus, so we have to put another minus, right? Times 1 transpose. Right? And now there's a term in G, which is minus on both of them, minus, and now we get alpha log n over n plus beta log n over n, GG transpose. Right? And now we have to understand the spectral norm of this matrix. Okay, so actually, we know that we know that nothing has happened on GG transpose, and in fact, right, this term is exactly the same as this one in terms of its spectrum, right? Because remember, the spectral number of this is n, so it sort of cancels with this n, so we get exactly alpha log n plus beta log n, which is the same thing as here, right? So this has a bunch of eigenvalues at alpha log n plus beta log n, then in the direction of G is an eigenvalue at 0, and we're subtracting something that is smaller, right? Because, I mean, it makes more sense to divide by n here, right? So that this now has spectral norm 1, to take away this term. Right, and if we do that, then basically we see that at the direction of 1 transpose, eigenvalue is worth alpha log n plus beta log n minus a smaller quantity. So it's still positive but smaller than this. And then G is just 0. So in particular, it means that, sigma squared is smaller or equal. The spectral norm of this quantity, what it is just alpha plus beta log n. Right? So we can use our inequality with this. We can use Bernstein's inequality with this quantity, alpha plus beta log n. Okay, so let's do it. So now, what t do we want to use? We wanted to use the t that was coming from our requirement, that we needed the LSBM, the norm. So let's write it. So now using Bernstein, using matrix Bernstein, following that the probability, right? The probability that spectral norm, again, we're using matrix Bernstein both on the smallest eigenvalue and the largest. Okay, this is bigger or equal than. Now the thing we needed was alpha minus beta over 2 log n. Let's do that. Alpha minus beta over 2 log n. Right, this is our t. This is now smaller or equal than. Okay, there's a factor of 2 because we're controlling both the upper side and the lower side. A factor of d, which here is n, because the dimension of our matrices are n by n. Exponential of, and now a big term. So now we have to do alpha plus beta squared log n squared, right? Because it's this. Oh no, it's not that. It's this squared. Sorry. So we get it's t squared. So we get alpha minus beta over 2 log n squared. Right? Log square n. I should make clear that it's not log of n squared. And then we have 2 times that quantity, alpha plus beta log n, plus 2/3 times 2 times t again, right? So t is again alpha minus beta over 2 log n. Okay, so let's try to simplify this a bit. Right? So now if we simplify this a little more, right? What is this equal to? It's equal to 2n exponential. Okay, and then okay, so let's see. We need to take a fourth out of the picture here. Right, so we multiply by 4 everywhere, so we get minus alpha minus beta. And the log n's, this log n squared cancels each one of these log n's, and 1 log n is left. Okay, so let's see if we can do this one at a time. I'm going to move the log n over here. Right, so we multiply by 4 everywhere, so we get 8 alpha plus beta. Right? Now the log n is disappearing because this log n squared, one of them cancels these 2, right? And now we multiply by 4. These 2 cancels with this 2, and this 2 becomes an 8. So we get plus 8/3 of alpha minus beta. Okay, so it's starting to look nicer. But now, what is this? Now we can have, there's a few ways of thinking about this, but we can move the n inside. So we can do 2 exponential of, right? Now this is what? This is minus. Right? Let me write it this way because maybe it's more clear what's going on here. Right? The n multiplicative outside comes as a log n inside the exponent that is additive. So it's exactly this. Right? I mean, another way of writing this, I'm just sort of rewriting, but of course it's the same way as taking 2 times n to the minus and then this quantity here. Right? I mean, I won't write it again, but this quantity here. Right? And so in particular, it means that if this quantity is positive, if this is positive, then the probability that I go in a deviation bigger than what I'm allowed to goes to 0 as 2 to n to minus some power. Right? So immediately what you get from here is a theorem, right? Which is that as long as, so as long as this quantity is positive, meaning that this fraction is bigger than that, meaning that this numerator is bigger than the denominator. So as long, as long as, it's better, so as long as, now what is the condition, right? This needs to be positive, so this needs to be bigger than that. Oh, there's a minus here, of course. Because of the minus here, this becomes a minus over here. Right, I mean, this is just calculation, so very prone to mistakes, but I think this is right. Alpha minus beta squared is bigger than 8 alpha minus plus beta plus 8/3 of alpha minus beta, then as long as this is satisfied, then the probability of going in a deviation bigger than this amount goes to 0, like 2 to the n to minus some number, right? So it's going to 0 very quickly as n goes to infinity. And if this is actually smaller than that, then we know the STP does exact recovery. So what we proved is then GG transpose is the unique optimal of STP with probability some bigger or equal than 1 minus n to some power, or some epsilon bigger than 0. Right, so the probability going to 1 as n goes to infinity. Okay, and this is not quite the same, this is not exactly the same as the optimal threshold, right? This is a different threshold than what we saw was the threshold of square root alpha minus square root b being bigger than square root 2. Right? It's not the same one, it's off by maybe like a factor of 4 or something like this. But the point is that this is an extremely versatile technique, right? Like the things that we did, we can do for many, many different models. And controlling the spectrum of these types of random matrices, we just used an off-the-shelf tools like matrix, for instance, can be used in a huge variety of applications. You can use it to understand the performance of algorithms in many, many, many different settings, like matrix completion, many, many others. And the nice thing is, the proof here is sort of completely standard. I guess now we think of it as completely standard that, building this little certificate after the fact became sort of clear that it needed to be this, then controlling for this, we control the fluctuations on the spectrum of this matrix using standard techniques. Now, it is actually true. One can prove a much stronger result than this. One can prove a result that STP works exactly at this threshold. It uses more sophisticated techniques. The idea basically is that the diagonal of this encodes, right, the in degree minus out degree. So the diagonal of this encodes when is it that a node is more in degree than it has out degree. So actually it encodes exactly this threshold. And it turns out that the off diagonals, because in the off diagonals entries are independent, can be treated in sort of with different techniques that are much stronger. They don't lose this logarithmic factor, right? This n created some logarithmic factor that we talked about when we talked about non-communication and so on. It's possible, just like in the Wigner matrix when this log n didn't belong, it's possible to control the off diagonal in a way that they exhibit even much, much more concentrations. And then you study the diagonal separately, and the diagonal reveals exactly this transition of the in degrees minus out degrees. So I mean, it's a little more technical and a little more sophisticated, but you can actually prove that STP works all the way to the optimal threshold. Moreover, the STP sort of, the condition of the STP reveals very naturally this in degree versus out degree, right? The place where the in degree stops being bigger than the out degree. But the nice thing is that this proof technique gets quite close. I mean, a priori proving that the STP does exact recovery, even in any of this regime, seems complicated, right? Because the STP, the graph still, of course, has some noise. So the fact that STP completely ignores the noise and matches exactly the truth, right, is still quite surprising. And one can show this using completely standard techniques. And another nice thing is that this is a very nice illustrative example of the applicability of matrix Springsteen, because this didn't even look a priori like sums of independent random matrices. However, if you massage it just a little, you get that it can be cast as matrix Springsteen, and you see that the loss that it has is just sort of maybe multiplicative factor of 4 or something like this, right? You're still, if you draw this region and this region, they look together in the plot, and you don't change as n goes to infinity, they're different, right? So asymptotically, you're still getting sort of the right, the right order optimal results. Right? And so after this, then we're gonna get into dimension reduction via random projections and things like this. This is sort of the end of stochastic block model and community detection. We might see these techniques later applied to other problems. All right, thank you.